Okay, if you remember, we started to talk about decision trees. So, and we made a game. We made a game, and it was a 20-question game. And inside that game, we understood choosing the first node, the second nodes, and all of those things are very important because we have to look at the most important attributes. And we said that the best attributes that we can have is the one which can split the data into two. And we did another example and we saw that only splitting into two is not necessarily enough. It should be split in a way that they are also discriminative enough, right? And if you don't choose a very good attribute, if you don't choose a very good node, what will happen? We will not get to the result. If you remember, we started with until the question were not really very strong enough, and then we had to switch. And then Tavi came, the question were okay, but they were not consistent in the form that the attribute that we choose should depend based on the answer of the previous question. And then when we had the error, we got to the results. And we learned that which attributes are important and which ones are not very important. Now that we have gained something, we will continue by talking about how expressive the decision tree is. So we are starting to go a little bit into the algorithm now. And in order to do that, we are talking about some specific example. And we are talking about some Boolean functions. And the Boolean functions that we will talk are AND, OR, and XOR. Definitely there exists lots of other Boolean functions that we may even use them in order to talk about the points that we want to gain. So we are using these three Boolean functions. We start with the simple form, we go to the more complicated form, and what we gain at the end of the lecture is a very important conclusion for us, okay? Now, is there anyone who does not know what is AND, what is OR, and what is XOR? So we all remember what are these logics, right? So, the question, how does AND works? And imagine we have only two attributes for the AND. Like we have only two inputs. So the question is that when will A and B be the true? What is the answer? When both of them are true, we will get the result to be true. So the question is that how we can use this one by using a decision tree. So our aim is using decision tree in order to represent A and B. And in order to do it, definitely it's pretty easy. It's not with, let's say, node A. So how many leaves do we have? How many values do we have? 2, because it's Boolean, it's binary. It's true or false, right? So we put true, we put true and we put false. Now, we know that in two attributed and if one of them is false, what is the result? False. So if I have a false, definitely the result is negative. The result is false. I don't need to check anything else. Now, if the result of A is true, I have to go to the next statement, which is B. And I have to look at B. If B can be true, B can be false, right? So if B is true, what is the conclusion? A was true, B is true, so the result is true. But if B is false, the result is false. We understand that we can switch between A and B. I could start from B. Why is that? Why if I switch A and B, nothing will happen? Why nothing will happen? Because AND is an operator which is commutative. But being commutative is not something very important which results into you can switch. We will do an example and you see that switching, although they are commutative, switching will not really result into something very important. So here in AND example that we have, it doesn't really matter if we are choosing B as the first thing or A as the first thing. It will not change our tree at all. In other words, if I just delete this one, and delete this one, and write B here, and A here, nothing will happen in the decisions. Do you agree? Yes. So it is easy to see. So, but in general, changing the order can affect on our tree. And sometimes changing the order will make maybe the tree to become better. What is the meaning of better? It means the computational complexity is lower, we will get to the results faster, and all other things. Sometimes changing it will make the tree to become worse. Let's get back to that 20 question example. If you remember, we had this example that most of us, when we were asking the question, we tried to divide into whether it is alive or if it is dead an object, right? So because it was discriminating very well. But if we had the question like, can we fit it in the classroom, was not a very good question, although it can be a very nice question if before you had so many questions, you already had narrowed it down, so then asking it whether we can fit it in the classroom can have a meaning. But if we put that question at the beginning, we may go to totally irrelevant part. Do you get the point? So sometimes changing it will make us to go to a better tree and get the results much faster. Sometimes it won't. It will become even worse. And as you can see, in some occasion, it won't change at all, like A and B. Now, let's do another one, and let's pick up OR and see how OR works. When do I have OR to become true? One of them is true, is enough for me to make it true. So, let's see. I have A, and I have B. And I start with the A. I start with the A. If A is false, what do I get?
We still have to check.
It can still be true.
If A is true, if A is false, I cannot get to a decision, right? I have to look at B because B can be true. In other words, if I am using exactly the same tree as I have in the AND, I cannot get to the conclusion, right? In other words, look, if A is true, I can check at B and I can make a decision, right? And if A is false, I do not check anything, so I do not get to the result. Can you tell me that apart from being false here, what is the other problem with this tree? You know that if A is false, because I'm not checking, so it's a failure. But what else is not correct? Is not the true word. What is also kind of redundant in this tree?
The right part, if A is true, it's already true.
Yes, if A is true, already I know this is true. I don't need to check B. B is true, very good. B is false, again, very good, I'm already true. Can you tell me that how can I fix this one? If I interchange these two, I can get the result perfectly, right? Because if this is true, what happens? A is true, I don't need to check B. But if A is false, I need to check B. That's why that here, if I am switching these two, I can easily get my results, right? However, if similar to AND, if I am switching these two, nothing will happen. I can still get the same result that I know, that I had. And one other thing is, like AND, how many nodes do I need to represent this one? Only 2 nodes. I need only 2 nodes in order to represent it. For the AND, also I need to have 2 nodes to represent it. Okay? So, I am dealing with the Boolean function. But when I am changing my AND to OR, I need to change some parts of the tree. Now let's continue by having a bit more complicated logic. Well, it's simple, but compared with the AND and OR, it's more complicated. And the question is that when do I have A, X, or B to be true?
When just one of them be true and one.
Then when they are opposite of each other, I will get true. When both of them are the same, I will get false. In electrical and electronic engineering, when we have a classroom like this, or when we have a room like that, and we have only one light, this is very normal that I have a light, a switch in this door, and I have a switch in another door. In other words, I can come here, I can turn on the light, and then when I'm leaving from the other door, I can switch off the light. In electrical term, they call it Vivian type of circuitry. And in order, if I cannot see the light, imagine that I don't know if the electricity is in there, even if it's not a light. In order for me to see that the circuitry is working or not, I have to look at the both switches. If both of them are in the same position, what does it mean? It means it is off. In Vivian, like XOR, it's XOR. They have to be in opposite situation. If one of them seems to be on, the other one seems to be off, it means the circuitry is on. If both of them are in the same situation, it means you don't have an electricity inside your, if it is a lamp, or whatever device it is in there. So XOR, this is the XOR logic. XOR, if they are, both of them are the same, I will get false. If they are different, I will get true. In daily life, in English, we are using the word and or quite a lot, right? Do you use XOR when you are talking?
I think our normal OR is XOR.
Yes, we don't say XOR, but our OR is basically XOR. Do you want to eat chicken or fish? Do you want to go to the bowling or cinema? So you cannot have both of, I can have both of the foods, but in general, when we are saying OR, we mean XOR. Remember, in XOR, we are picking one of them. One of them is true, the other one should be false in order to get it completely true, right? So this is very important to keep it in our mind. Anyway, now we want to make a decision tree in order to give us the results. I start with A. A is Boolean, so I have only two values, true and false. If A is true, what is the decision? What is the decision? No decision. You have to look at B. A is false, cannot really tell me anything. I have to look at B. If B is false, definitely I am false. If B is true, definitely I am true. Now, what if A is true? Again, we cannot make any decision. I have to look at B. If B is false, this is true. If B is true, this is false. Now, when we are looking at this one, we see that this is something that in graph theory, they call it a full tree. This is something, have you all taken a course called Digital Logic Design? Have you taken it? Yes. Okay. Do you know, when you look at this one, what comes in your mind? There was, do you know this? Truth table. It seems that here I have the full truth table of the logic of XOR. Look, false, 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 true, true, false, true, true. Whereas if I look at the and or, I can see that for one of the branches I don't need to have the full run to go down. Because if I know in the and, one of them, the first one is false, the result is false. I don't need to check the next second one. Or in the or, if the first one is true, I don't need to check the second one. I know that the result will be true. Whereas in here, I need to have the full complete tree in order to make the decision. So this is something that we have to spend a moment and think about it. Now, we understand that we could represent and or as a full tree, right? I can do this one for the and. I can say A, false, true. I knew that this answer is negative. If this is true, I have to look at B. If this is true, it is true. If this is false, this is negative. But I could also, instead of writing negative here, I could say that no, I want to check B. And if B is false, this is false. If B is true, this is false again. Right? I could do it. And I could do the same thing for OR. And we can understand that for XOR we cannot do it. And what we do, we have to use the full truth table for XOR. Okay? Now we have a quiz, which I did it. And the quiz was represent and OR in your notes as a full tree. And can you do it for OR? Probably no. What? Do it. There is a point behind it. That's why we want to see. We have seen that for and OR, I could use only two nodes. But if I want to represent it as a full truth table, there exist some other nodes. And we understand that the difference is this. Right? The difference is that I have that blue stripes also true. The reason that I thought we'll do it is this. We can see that in the generalized for and OR, I need to have three nodes. I can simplify it to two nodes. And this is, as I can say it here, we cannot really see it much. What is the difference between 2 and 3? They are very close to each other, right? So in order to understand what is really going on with the tree, let's do it with multiple inputs. And by multiple inputs, I mean like we have n attributes, and n is greater than 2. Let's say, I don't know, 100 attributes. And let's see how the things will look like. So, assume we have an n OR. Do you know what is n OR? It is an OR which we have n inputs. And we understand when we are talking pattern recognition, n input means n attributes, okay? And if we have n OR, this is a very famous function, and we call it any function. Why we call it any?
Because
if any of them is true, the function is true, right? So we call it any function. And in the any function that we have, and if one of them is true, we will get it completely done. Now, any idea that how the decision tree will look like? In other words, how many nodes do we need to have in order to represent that n OR? N nodes. How does it look like? Please draw it. Yes, Eric. How does it look like? Now, if we look like something like this, A1, if it is true, that's positive, right? If it is false, I check A2. If this is true, that's positive. If this is false, I look at A3. Till I get to AN. If this is false, it is negative. If this is true, this is positive. So as the question asks, how many ends do we have and how many nodes do we have? N nodes, or we have n attributes here, right? So, because we have n nodes, we call it that the size of decision tree is n and it is linear. Why? We have n nodes, sorry, we have n inputs and we have n nodes. Life is not that much easy. Life is not that much easy. We understand that this is for OR, and what will happen if I change it to AND?
It's just fit the edges.
Yes, we have to fit the values from true to false, but we will have again n nodes and it is linear. But the life is not that much easy when we need to have, like, let's say, full tree. And we want to talk about n XOR, and XOR which has n inputs, okay? And in general, this is called a parity function. When we are dealing with OR, we were talking about any function. Here we are talking about parity function. And again, in logic design, you might remember that parity functions, we do it in the internet connections. We are doing this parity check. It's very useful to see if the package has been transformed completely or not. But when we are talking about parity, we have two types of parities, right? Do you remember them? Odd parity and even parity. And usually we say that if it is odd, we call it true. If it is even, we call it false, right? And what we mean by true and false, like by odd and even parity, is that if the number of true is odd number, we call it odd parity, which is true. And if the number of true in a sequence is even number, we call it even parity, which, let's say, it is false. Okay? So are we together regarding this parity? So XOR is called a parity function, and we have two types of parities, even and odd. And the even and oddness comes from the number of true that we have in a sequence. Because look, here I have, let's say, n sequences, right? So I can see how many trues or false I have in here. So we will pick odd parity as the parity that we desire, and we introduce the odd parity to be true. And let's look at the question. The question is that, how does this decision tree now look like? That one was pretty easy, right? The question is that, how does this one look like? For n inputs. Yeah. 1 minute. Try to draw it. I can see there are only a few people who can draw it correctly. One is Eric, the other one is Suman, because we don't have space to draw it. Here I have enough space to draw it, but in here I won't have enough space to draw it for n. In order to draw it, in order Eric uses his pen, I need to reduce this number. So let's do it for 3 variables. And let's draw it for 3 variables. And you will see how big it is. And when I say n, basically we don't have space to draw it. So let's do it for 3. So A1, it can be true or false. If it is true, I will look at A2, which can be true or false. If A2 is true, I have to look at A3, which can be true or false. But if A2 was false, I could still look at A3, which can be true or false. At A1, I was talking about true, but what will happen if A1 is false? Then I have to look at A2, which can be true or false, and for each of them I have to look at A3, which is true or false. Right? And even with 3 of them, likewise, I already got out of the space. And if odd parity is something that I worship, can you tell me that what is the result? Here, let us start from left to right. This is true. This is false. Why this is true? Because I have 1, 2, 3 truths. 3 is an odd number, right? Here, why it is false? Because I have 1, 2 truths, and 2 is an even number. What about here? It is false again because I have 1, 2 truths, and it is an even number. But here, when I come here, I have only 1 true, which is, make it plus. What about in here? False, because I have 2. What about here? True. Here? True. Here, false, right? So this is how it looks like. Now, Eric, how many nodes do I need?
7.
How many attributes did I have? 3. Any suggestion that what can be the relation between the number of nodes and number of attributes? It seems to be if I have an n attributes, I need to have 2 to the power n minus 1 nodes, right? Is it linear? 2 to the power n. And it's straight that I'm not linear. So it's not linear, and the number of nodes that we have is 2 to the power n minus 1. 2 to the power n minus 1. I have 8 input. Can you tell me that 8 attributes? Can you tell me how many nodes do I have? Do I need 255 for only 8. So you see that it is growing very fast. It is growing very, very fast. Now, 2 to the power n, when you want to talk about the computational complexity of this decision tree, when we have n input, we say that it's capital O 2 to the power n, right? So capital O 2 to n is the computational complexity of such decision tree. Now, if so that is a full tree for XOR, for parity check. But parity check is very useful. As I said, it is one of the best way of checking if the package that you have received is a correct one or not. In your printer that you have, we are checking the parity. We are checking that all the bits that we are sending have been received completely correctly or not. Now, but in order to solve it, not many people will use that one. We understand that as the number of attributes increase, this tree will become bigger and bigger, and it will become a big mess. So what we do, we are changing the way that we are representing. In such a case, we understand that I can define true to be 1, false to be 0, and I can only add the numbers, right? So I can look at the summation of the numbers. So I can change the whole strategy, and by looking at the summation of the numbers, decide whether it's an even number or odd number. And this means that I can change the tree, and I can make the tree much, much simpler. I can check if it is even or odd, right? So I can have one number, one node, and I can have 2 values, even or odd, finished, right? Instead of having 7 nodes. This is called, in artificial intelligence and machine learning, this is called cheating, right? And this is a good way of cheating. This is the thing that we try to find out how we can do this cheating to have a big tree much smaller. Remember the AND gate, the OR gate? It was also kind of a cheating because we knew that if one of the nodes is true, I don't need to look at the other ones. It will be true in case of OR, right? Or if one of them is false, I don't need to check the rest. In case of AND, it will be definitely false. So the challenge here is that how we can do this representation, how we can do this type of cheating. Now, we understood XOR was very hard, right? And at the same time, we also understand that OR or AND are pretty easy. So the question is that how expensive is this decision tree that we have made? So not all the time we are dealing with an easy situation like OR and AND. We are dealing with XOR and XOR type questions actually quite frequently. So, and when I am giving you the question, when you are answering the question, we really don't know what is the results, right? In case of XOR or similar type, we don't know. We have to go through all the nodes to find out what are the possible decisions. Now, the question is just how expensive the decision tree is. And in order to talk about this one, we say that let's consider our n attributes XOR, n XOR. We have n input. We could not draw it because we don't have enough space. Now, in such a tree, Suman, how many decision trees are there? And I have made it much simplified. We assume everything is Boolean, the output is Boolean, so we are only dealing with true and falses. So, question, how many decision trees are available here? I give you everyone. I give you 1 minute. And after that, one by one, I will ask you your opinion. How many decision trees are in the n attributed XOR? Think about it. Okay, Anton. We start from you, and we come back, and we finish by Michael.
I can imagine how can we draw another tree from this one. So I guess 1.
I also think 1, but I'm not entirely sure what your question is really.
No, then if I have n, what are the different way of combination that we can have?
Like one tree in different ways.
Yeah, I mean, this part is going to have only one tree, right? Because I can have a tree which says that I am looking for only all the bits are true. So A, if it is false, decision is that you are not in my class. If A2 is false, you are not in my class. You know, I can have it binary from that sense. So how many trees can I have?
I would say
Infinity. So if I have 2,
we can use Boolean function and we can make them long.
I have only 2 nodes. Or even simpler, I have only 1 node. Do I have infinity?
Yeah, but if we use like OR gate and other gate, we can connect them.
It's XOR.
Okay, like we can make XOR with an OR gate, like in digital.
You didn't get it. I have an XOR and I have to make true or false. If I have only 1 node, we understand that it can be either in the class true or in the class false.
This is the different tree. No.
I'm not talking about how we are making the XOR. So on. If you want to quickly answer, the answer will be a lot. And I mean it by a lot because now let's calculate how many we need to have. At the beginning, how many attributes do we have? N. N. And I pick N, I pick A1, and I already decide if it is in the true or false. And when I go down, how many attributes do I have? N minus 1. And as we are going down, it seems that we have n factorial combination of these nodes in here. Right? And this n factorial is actually for building nodes. And this is the order of the computational complexity for making the nodes. I have not made the decision yet. I have not found the decision yet. I have only built it. And if I want to make the decision, we already saw that this is exponential, isn't it? It was 2 to the power of n. So, let's change the question in this form. Same question, but I'm changing it, but the result that we will get, I'll get back to the previous slide, we will see that it will be the same. And it is like this. Then we have a Boolean attributes of from A1 till AN, okay? And I have a truth table, which definitely will look like that. One of them is everything is true, the other one is everything is true except this one. You know the truth table, right? Is there anyone who has never seen a truth table? Okay, good. So I have a truth table like this one. So the question is that how many rows will I have in this truth table? Let's make it also as a quiz. Think about it. I have n attributes and Boolean inputs, and I'm making my truth table. The question is, how many will I have? I give you 1 minute to think. You have 5 more seconds to calculate your answer.
Do you want me to answer?
Yes, I want you to answer.
2 to the power n.
2 to the power n, not n. If I have only one input, how many rows do I need to have in my truth table?
I thought it's just for like one of them is false and the other is true.
So,
We are just comparing.
Look, if I have a truth table, right? Do you remember the NOT gate? Which we are showing it like this. And we write here x and x bar. What are the values that we put here? And 1. So only one input. How many rows do I have? 2. If I have 2 inputs, if you remember for 2 inputs, right? It was x and y, and we were saying that we have something like that, right? So for 2 inputs, how many rows do I have? 4. If I have 3 inputs, I will have 8. So if I have n inputs, we can generalize it that I will have 2 to the power n rows, right? I will have 2 to the power n rows. And it means it is growing quite fast. Now, the next question that we have is how big actually the whole truth table is. And in order to answer that one, we know that we will have 2 to the power n different possibility of this choosing of this instance, right? If you want to build your tree, we know that, not build your tree, build your truth table, we know that we will need to have 2 to the power n different possible instances. In other words, we need to have 2 to the power n rows. Question is, how many different ways might we fill out the column, the left column of the output that I had in the previous table? So 2 to the power n different possible instances we might be seeing, right? In other words, we will have 2 to the power n rows. Now, how many different ways might we fill out in the column of the output? N multiplied by 2 to power n. Oh, okay, let's make it quick. I can have 2 to power n different instants. And I know that each output can be either true or false. How many ways, how many outputs do I have? 2 multiplied by 2 to power n, which means this is what hypothesis I'm writing. This is what hypothesis. So it's not related to me. Just 2. I don't know him at all. Look, I'm actually telling you the answer. I have 2 to power n instant, and each output can be only true or false. So I will have 2 to power 2 to power n possible output. And this is a double exponential. Look, it is not 4 to power n. It is 2 to power 2 to power n. Do you want to see how big it is? If n is equal to 1, it is 4. Why? Because I can have 2 to power n way of putting the stuff, and then when it was 2, I understand that this is 4. If n is equal to 2, I have 4. If n is equal to 3, I have 256. Can you calculate if n is equal to 6, what is the number? 6. Do you want to use a calculator?
Yeah.
I don't think that you can calculate this number.
It might.
I wish I had that many cents. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 digits. Okay, it's still less than Avogadro number, but so we can see that, you know, 2 to power n was exponential, it's double exponential. 2 to power n by its own was bad. So this is bad. This is a serious issue. I mean, apart from the smile that you have, you should understand this is a problem that we are facing. That's why the representation of the data is important. That's why the tree is cool, but why not every time you can use it? Because there exist such problems. Now, we did this calculation because we wanted to see something very important, and what we wanted to see was this sentence. Decision tree is very, very expressive. And it was like 2 to power 2 n. And the question is that now, among to this one, which tree do we have to choose, which we can get to the decisions very well? In general, we have to go through all of them. Sometimes we don't have any alternative, we have to go through all of them. So people are developing an algorithm which you can search through these trees very quickly. You can traverse through these trees very quickly. So we have to deal with how we can represent this data. Supposed to go to the next slide. Now, right now, you understand the problems, the issues with the tree. You understand the number of outputs that we have, and why we call it double, super double, I mean those big numbers. You also understand if you want to make the tree, what is the best attribute from the 20 question game. We understand that what is the 20, what is the best attribute. Now that we have good knowledge, like we can say that, hey, decision tree, you are a good friend, then we are ready to have to talk about a very famous algorithm which is called ID3 algorithm. Okay? And this is something that we will talk about on the next session. So on next session, we will start to talk about the ID3, and then we will talk about the continuous decision tree, and then we are ready to go to talk about regression. Do you have any question? If you have no question, this is the end of the lecture for today. We'll stop the video.